All right, so hello everyone. My name is Kirill, as most of you know me, and today I'm really glad to introduce Federico Bianchi, who's a senior machine learning scientist at Together AI. He's working on self-improving agents. Previously, he was an AI engineer at OpenEvidence and a postdoc at Stanford University. His work has been published in major journals such as Nature, Nature Machine Intelligence, and Nature Medicine, and conferences such as ICLR, ICML, and ACL. And today he's going to talk to us about very exciting work that they published together with Stanford. This is about the paper Learning to Discover at Test Time. So without further ado, Federico, the floor is yours, and thanks a lot for taking the time to talk to us.
Yeah, thank you so much for inviting me. I'm excited to be here and talk a bit about this work. Thank you for the introduction. So today we're going to talk about learning to discover at test time. This is a joint work with a couple of people from different places: Stanford, NVIDIA, the Astera Institute, UC San Diego, and Together AI, which is where I'm from. So let me see. Why is not? Okay, cool. So I'm a senior ML scientist at Together AI. As Kira said, I'm formerly at OpenEvidence at Stanford. I'm working a lot on general post-training and in particular on self-improving agents or self-evolving agents or LLMs. So I'm very interested in understanding how once we have a language model or an agent, how it can improve and solve novel tasks. And this is going to be the focus of today, which is going to be solving open problems, which are by definition open and still need a solution using AI and language models. So I want to give a very quick summary of the paper in 2 minutes, just to as an head start. The idea behind what we do is that we do reinforcement learning in an environment that is defined by a single test problem. Single test problem could mean many things. We consider mathematical problems, we consider kernel optimization, and if you take kernel optimization as a single test problem, what the environment looks like is you just want to optimize one single kernel. So you have your own agent that is gonna try to optimize the code of a kernel, and it's gonna get rewarded on how good the improvement it adds to the kernel are. And basically through this interactive improvement, the agent is gonna improve. So I wanna highlight two differences from standard RL that are gonna pop up in the rest of the presentation. And one of the differences is that the policy we are gonna train only need to solve one problem. We are not interested right now with generalization. We want to solve one single problem. And again, one single problem means we want to find a new version of a CUDA kernel, or we want to find a new solution or a new lower bound for a mathematical problem. The second big difference is that we only need one great solution. The policy is just a means to an end, which means once we have found our new artifact, we're gonna throw away the policy. We don't need the policy itself. This is kind of a framing difference. So in this problem, the focus is the artifact itself we generate, and the policy is not our interest anymore. We train this agent, but eventually we throw away the agent. And I have some related work here of possible interest. So the big difference that we introduced with our method that is called TTT-Discover is that our learning objective and the search subroutine are gonna favor most promising solutions. If you think about reinforcement learning, what you're generally trying to do is maximizing the average reward in general. Here, instead, we wanna basically maximizing the best possible reward, which brings us to add a change to our objective function. We have a bunch of new results in mathematics, GPU, kernel engineering, algorithm design, and biology that I'm gonna quickly showcase later. Cool. Let's start with a more general kind of introduction. There are two very important things when you try to address or solve an R problem. These two are search and learning. Think back when you were, for example, a student and you were trying to solve some of those textbook problems. I'm sure that like you stumbled upon some of them, and even if you had studied, even if you had followed the lectures and you were sure about your capabilities, some of those problems were very hard to solve. The reason why these problems are very hard to solve is because it's because they kind of do not resemble anything you have studied before. You need some trial and error and searching through different solutions to actually find a solution. This is actually how we solve this kind of problems. You have, I don't know, you have a proof that you have a mathematical statement you will try to prove. You try a few things, they don't work. Eventually, your learning paradigm is going to improve and you're going to eventually find probably the solution. So it's something that requires some work that combines learning, so learning from your mistakes, and searching through a set of like possible exploring solutions. So the idea here is that like some problems cannot be solved by first attempt intuition, and the progress is gonna come from iterating and learning from what fails, which is very important. We should learn from the mistakes, and this is gonna be the core part of like the learning of TTT-Discover. You probably could represent the learning loop in a way that looks more or less like this. So we have an art problem. We try to solve it. So we have a first attempt. We evaluate our attempt. If the evaluation is not somehow correct or we have a problem with our attempt, we try to refine the strategy. This brings us to produce new attempts. And eventually, hopefully, after a while and after like refining our strategy a bit, we're gonna get to a breakthrough. So we focus on open problems, and the definition of the open problems we want to try to solve is problems in which even somehow small numerical improvement actually carry real weight. So even modifying things a little bit can potentially have a big impact on the frontier of what is known. An example is like GPU kernels. If we are able to optimize even a single kernel by 5%, that is a huge improvement that is propagated to a tons of neural networks. So, if we assume that humans improve by combining learning and search, or learning from attempts and search, how do current AI discovery systems improve? Or more in general, how do current AI systems actually try to solve problems? And a very nice example of a system that tries to discover new things is AlphaEvolve. AlphaEvolve was a system introduced by Google DeepMind now almost 1 year ago, because it was like 2025, I think it was August or around that. The idea was that they built this very big system that used their frozen Gemini's model to solve problems, and it's probably going to work more or less like this. You have a human that is going to define a target, so a problem, some evaluation criteria, and so on and so forth. And then the system is going to go through the process and try to find a solution. So you have a set of sampling prompts, you have a set of LLMs that is going to get those prompts and come up with solution to one of the problems. You're going to have an evaluation phase. The evaluation is going to give scores to each of the states. The states that the model has generated go into a program database, and these states are going to be sampled according to how good they are. And eventually, through this kind of loop, you're going to get improved state and so on and so forth. So you have this kind of like cyclical way of coming up with a solution. AlphaEvolve was incredibly successful in finding new results across a wide range of mathematical problems. Here, there is the paper from, this is from the Terence Tao blog post, but they also have a paper, but this image is from the blog post. And the image basically showcased the 67 problems that they tested, and some of the problems in which AlphaEvolve was able to improve a known result in mathematics. So it's been a very successful endeavor. And if you think about this, is very useful because like a lot of like these problems require a lot of human knowledge and years of PhD studies to be improved. And now we have the possibilities of having LLMs support us into coming to solutions. So We don't have access to AlphaEvolve, but we have access to its open source somehow version, which is called OpenEvolve. And I just want to have an example of like one of these problems to give some additional context on what we're going to talk about. So this is called the circle packing problem, in which like given 26 circle in a unit square, we want to maximize the sum of the radii. And this is an example of the image that I got from the OpenEvolve blog post. So OpenEvolve is gonna more or less work like this. So you have a set of you have a program database that initially might be empty or might have an initial problem. You have some sampling of the prompt. You have an LLM that comes up with a proposal, which can be like new ways of solving this problem. You have an evaluation phase to see how good the solution is. The states go back in the program database and so on and so forth until we get the best program that hopefully improve the state of the art. This is how the evolution kind of looks like. This is the initial solution, for example, from OpenEvolve. You see that basically it's generating a very straightforward representation for this circle. But as time goes on, the solution get more complex until what OpenEvolve does is generates a code that is gonna define a minimization objective that has to be actually improved so that like we get the actual correct circle packing. So you see that like through this kind of optimization in which like OpenEvolve is gonna edit code or edit like an object itself, you see that we go from this representation in Python to a more sophisticated representation. And both AlphaEvolve and OpenEvolve works on code. So they generate code that is gonna be reshaped and is gonna bring us to a new solution. So two limitations to keep in mind here or like one limitation to keep in mind here is like we have search that improves the candidates, but there is no learning happening during the run, which generally means that like your model is kind of doomed to make the same mistakes over time. One example that I have from experience is that if you ask LLM to generate code that doesn't time out, often the model will still generate code that actually timeouts because it takes too long to run. And without learning, it's very hard to force the LLM to generate code that doesn't time out. Instead, one thing that we actually observed is that through learning, if the model is rewarded negatively for generating code that actually timeouts, the model eventually learns to time its own code and exit the training loop, for example, before something bad happens. Cool. Let's now work on the discovery problem. And now I have like a definition for this problem. So this is the formulation very similar to the AlphaEvolve 1 in general. So given a scientific problem description that is going to be referred to as D, we have states, and which could be like, for example, a new kernel. We have actions, which could be like model outputs, so a language model output. We have reward function that are gonna reward our state, and we have transition function that are gonna allow us to go from the actual action to the actual state. We define discovery as the event of finding a new state for which we get a reward that is higher than the reward from the state of the art. So just to break this down a little bit more, the state is kind of a concrete candidate at a current step. If we are doing kernel optimization, for example, we have this kernel that is one of the kernel we basically optimize. So it's all the code from the kernel. The action is going to be the actual output from the language model, and this is going to look like something like a set of probably thinking tokens if we are using a reasoning model, and an actual answer that contains the code. So as you can see, the answer contains the code of the state, and this basically allow us to move directly to the next step, which is the transition. And the transition is basically, in our context, the parsing of the code. So we take the action from the model and we extract the code, and then optionally we can execute. This depends on like if we need to execute to get a reward or not. And finally, the reward is our continuous and verifiable score that is gonna give us a value for a candidate state. And in this context, you can say that the reward for the kernel could be 1 over the actual runtime of the kernel itself. So we have this set for the discovery problem, and now we're gonna go into how to actually find the solution to this problem. So we have a few different methods for search that are basically readily available for us to use. And the simplest one is best of n, like I'm sure everyone has done to solve problems with LLMs. So you have a original problem or a general query, which could be find a new kernel for this operation. We generate n candidates. We evaluate all the candidates using a reward function, and then we select the best, and this is our best solution. And this is the standard best of n, also used to do training for distillation through rejection sampling, and so on and so forth. The pseudocode version of best of n looks like this, and I'm gonna keep this so like we can keep the comparison for the different algorithms. But the idea is that like you take an input a problem, a policy, and you have probably a starting state from the state of the art. And then for each of your rollouts, you are gonna basically sample from the policy condition on the description of the problem and the state. You're gonna get an action. You're gonna apply the transaction function. You're gonna apply the reward function and get a new reward. And then you wanna return the state that gives you the maximum reward in the context of best of n. So this finds probably promising direction, but might fail to fully exploit it because there is no state reuse. So the next addition we want to put on top of this is basically state reuse. And the general intuition is that like we want to keep a buffer of good states that we're going to use to resample from. So we have a problem as before. We have a buffer H that contains the states. We're going to sample from the buffer and ask an LLM to provide with newer candidates given the influence of the buffer. We are going to get all the different scores. And then we're going to select the best one, and the best one or multiple of the best ones are going to go back into the buffer, and we're going to start sampling again, and so on and so forth. The idea here being we're basically making this evolutionary way of sampling across candidates so that we can build up a better solution. And this is the pseudocode. You see that like the only difference here is that like we added a reuse function to sample, and then H is gonna be our buffer. So we're gonna sample a state from H, and we're gonna condition the policy on the sample state. Again, here before we just had the state-of-the-art state, but now we have this adaptive state that is gonna influence the future actions we find. Cool. Now, what is missing from all of this is training, which is essentially what we do here. This is TTT-Discover, and the only difference from before, the main difference from before, is that now we are going to train the parameters of this policy. So the policy is not frozen anymore. We're going to train on top of it, and the idea is that like we're going to train so that the language model can now learn to distinguish bad completion from good completions, and we want to basically downweight all those bad completions. The example here could be timeouts, or for example, solutions to the problem that are not actually efficient or effective. So the key difference here is that, as I said, we take the policy weights and we are going to update at each step using the experience from the rewards we get from sampling from the states. So again, let me go back to the things I said at the start. We are trying to solve one problem at a time. So the RL environment is defined by a single instance, and the policy is disposable. After we train, we're not really interested about the policy. We remove the policy, and we only want the new state that we're going to use for our purposes. So can we use naive reinforcement learning for this? And this is gonna bridge us to the two additional things we do to improve learning and search on TTT-Discover. So naive RL is gonna optimize for average performance, while Discovery needs to optimize for the maximum. There is this problem of like short horizon. So starting from scratch every time, as we saw in best of n, limits how far the policy can get, and we need to extend the horizon as much as possible for this to be successful. And finally, the policy might collapse to safe action, so we need to basically like use reuse to basically exploit the best states as much as possible. So two things that we do, one on the policy level and one on the reuse level. We basically need this objective that is gonna basically favor the maximum, and then we are gonna basically use PUCT to balance the reuse and the exploration. So these are the two main changes. One, we're gonna use the entropic objective that is gonna favor a maximum reward, and the second one is that we're gonna use this PUCT reuse kind of strategies to explore, to balance exploration and exploitation. Cool. Let me start from the entropic objective. So as you know, the we in naive RL we are gonna try to maximize the expected reward, but we care about the maximum. So what we do is that like we basically implement a different objective that we call the entropic objective, which is basically reweight for this beta parameter for the reward. The idea is that like as beta goes to infinite, the objective is gonna tend to max instead of the expected value. High reward action are gonna be weighted exponentially more in this context. Beta is set adaptively per state. The details are actually in the paper, and I'm not gonna mention more about this, but I wanna give the intuition of what this does. If you have these five rewards and different weights for each reward, so 2, 4, 6, 8, 10, you can see that the relation between rewards and weights after normalization is linear. But when you use an entropic objective, what you do is that like you basically skew the weights toward the action that had the maximum rewards. And this is the core part of the algorithm. We wanna get the reward that get the maximum. Sorry, we got get the action that has the maximum reward. Again, this is important because discovery allow us the focus of discovery finding the best possible reward or the best possible state to which the best possible reward is associated, and the policy itself is not important. So we are less interested in training a good policy. We just need a policy that eventually is going to bring us to find the best possible state. The other thing we do is PUCT-inspired state selection approach to balance exploration and exploitation, and this is related to the Monte Carlo research kind of style sampling. I have most of this slide have related work to refer to for the inspiration from where things come from. The idea is that like we are gonna have a tree of states because like each state is gonna derive from a parent because like we always condition on the states. And the question is, how do we decide which state to expand next? And oh, wrong direction. So we use the PUCT scoring function in this context that is gonna be made by two components. One that is a pure exploitation component and one that is an exploration component. Here is the Q of S is gonna be the best reward found by expanding S, and this is the important part, is the best reward, not the average reward. So we exploit a state as much as is one of its state or one of the state of its children is good. It's not the average. Again, to bring again back to the difference between standard Monte Carlo research. And then we have like here a formula to basically reward some of the states for when they have not been explored enough. So the exploitation is basically gonna simply define the state that has to be expanded as the one that has the highest reward, while the exploration bonus, what it's gonna do is basically in this kind of like high level intuition picture, is gonna basically like reweights the second part of the formula by considering how much one state has been visited, and if a state has not been visited enough, we are gonna give more score so to sample it again. This is summarized basically by this plot in which, like as you can see, state D had a very high exploration component, exploitation component, my bad, But when we combine the exploitation and the exploration component of state B, eventually it has a higher score, so B is going to be selected to be expanded again. And through the balance of this kind of representation, we are going to find the best possible state at every time. Nice. So we train using GPU-SS 120B, so we do everything with open models. We use lower rank adaptation, 50 training step, 500 rollouts per step, and 32K context window. The eventual cost is around $500 per problem. And we have code online. We just released a few days ago a new version of the code that should be much easier to use if people are interested in trying this thing. And one other thing that I want to mention is that like we for training we use Tinker, so we don't try and model locally on bare metal kind of machines, but we use Tinker for the full pipeline of training. So what runs locally for us is only the environments. Nice. I have a set of results here that I'm just gonna showcase. So one fun thing about this project is that we try to solve problems we are not expert about. So most of the time we have to basically send the solution of this problem to expert for actual evaluation to ensure they were actually correct. So yeah, I have the Erdős minimum overlap problem and the autocorrelation inequality. These are two problems that have been approached also by AlphaEvolve and have historical kind of value. And yeah, I just want to show that like these are the step function that different models come up with for the Erdős problem. You see that we have been able to improve upon both the best human result from 2016 and the AlphaEvolve results from last year. And our improvement is 6 times larger than AlphaEvolve's improvement over the prior state of the art from the humans. And you can see here the comparison of the different step function used to evaluate the models. Similar for the autocorrelation inequality, you can see here that like we have an autocorrelation. We found a new upper bound for the autocorrelation inequality, and we also compare to theta evolve, which is another model that came up a few months ago, which improved some other results on the benchmark. So we sent this to a math expert, which was Professor Davide Torlo of Università di Roma La Sapienza, and he verified that our solutions were correct. We have a set of verifier to ensure that like these solutions to mathematical problems are actually real and not completely hallucinated. And this is like the evaluation from the expert. So another very interesting problem that I'm very excited about is kernel optimization. So the idea is that like we start from a starting kernel and we ask a language model to provide a new kernel for a specific operation. In this case was the triangle multiplicative update, which is a very important operation in AlphaFold 3 and a bunch of other models. So the state is Triton kernel code. So we compute the rewards over model. We use model for the reward computation, but we basically do our full loop and we train a model. We train on H100s and we evaluate on a set of different GPUs using the GPU model leaderboard, which is this, I guess, open challenge for kernel optimization. And if you look at the results, we find state of the art on all the Trimul benchmarks for all the different possible somehow combination here. An interesting thing is like our solution is 50% faster than the best human solution on A100s. You can see here that like we improved the kernel by 50%, and our improvement seems to transfer across kernel, which is very interesting because we only trained, or like at least our reward computation was done over only A100s. So there is this kind of transfer, so we learn this kind of more general properties. So what the kernel discovered here was like there were some every memory IO from element-wise operation, and so basically the optimization discovered by the model was basically fusing some of operation together and finding better approaches to do this. So here we reached out to the GPU mod folks for a review, And I think like the review here is interesting because like the solution is similar to current human solution, but executed a little bit better. So what humans didn't do that actually brought us a very good improvement was basically the fusing of some of these operations together, resulting in this solution we come up with that outperformed the baseline for a large margin. Another task we try to approach is the coder heuristic context. This is taken from a Sakana AI benchmark, the ALE bench, in which this is a benchmark for long horizon algorithmic engineering. In which you have very hard problems, optimization problems. So again, there is a continuous reward you can optimize on. Basically, you generate this piece of code that is going to find some solutions to the problem, and you're going to get a continuous reward from the leaderboard. So the two programming competition we tries are the AHC 039 and the AHC 058. One is more geometric and the second one is scheduling. And again, once we do our full loop with GPTOSS, we beat both solutions and we basically got to the first position in the leaderboard at this context as at this contest. We also compare with ShinkEvolve in this kind of context. ShinkEvolve was the evolutionary agent that was produced by the Sanaka AI folks a few months ago. So for both solutions, we get to the first place, and there are some interesting kind of like approaches that have been added by the agent by using beam search, greedy algorithms, and so on and so forth. So the one fun thing is always to look at like the different solutions over time and what the model is doing to basically improve each solution given the states from the past. Another thing we try to do is single cell RNA sequences denoising. So this is a task in which like we know that like data has some measurement noise and we want to try to improve this. We use the Open Problems benchmark, which is a very recent benchmark out there for evaluating the denoising algorithm. One very important thing to point out, this is a very experimental application. Our Discover algorithm, as I'm gonna show next, improves upon the state of the art, but benchmark metrics tend to be incomplete, and it's very hard to say that like we keep the biological validity for some of these downstream tasks. So again, disclaimer that like while we, as you're gonna see, we get the best performance here on a bunch of benchmark and compare with like state of the art algorithm, the results are open for consideration since we don't know the actual biological validity of the full algorithm. And actually, this is also what the expert reviewed said. This is Professor Erickson from MIT, and of course, the professor highlighted the fact that like we have a new algorithm that is good, but like improvement on metric for single cell data analysis task may not always be transferred to actually the ability to obtain new biological insight, which is often difficult to quantify and therefore actually benchmark. So the general idea here, we tested on only one data set, so we don't know if the generalization is actually biologically valid or just like a number on a leaderboard. Nice. We run some ablations and general analysis, which I think are interesting. I have some results here. So we wanted to see which of the different components were useful to getting the state of the art. This is on the kernel engineering task. So you can see that like using best of n never brings you far or like never gives you very high reward. Using some initial states with no test time training is gonna bring you somewhere, but the only way you can get to actually state of the art, the only two ways you can get to the state of the art is using the test time training discovery or a greedy approach. But test time training discovery is gonna get you a much better approach to find the best state. So all the things matter. Here are the score for the different for the different kernel for the same kernel optimization, but through a different view of the different things we had. So the entropic objective and the state reuse and the learning part are all very important things that allow us to get the best score. So when we drop one of the components, we tend to get lower scores in the final representation. So, and again, the best human is uh, 130, sorry, 1030, 1371, which actually is only beaten by the use of all our components together. Cool. Some limitations. So right now we have been focusing on continuous and verifiable rewards because like we basically hill climb on the continuous reward from the system. So we hill climb on the continuous reward from the kernel runtime. So right now the system cannot handle sparse or binary rewards, but also non-verifiable domains because there would be no way for us to propagate the actual feedback. In general, problems without clear reward signal or unstable reward signal are very hard to optimize on. And we have this future work in which we want to basically expand this to this binary word and see what we can do for non-verifiable domains. I'm actually very curious about the non-verifiable domains part. I think it's something a lot of like researchers are working on because it's very hard to doing RL with non-verifiable rewards. And so yeah, very excited to see what's the next step of this process. Um, Quick summary of all of our results. So we optimize on math, kernel, algorithms, and also biology. We get very good scores across the board here. And everything is done with open model. Sorry, skip one slide. Everything is done with open model, GPTOSS, $500 per problem with fixed hyperparameters. Again, we use Tinker for training. And two key takeaways here that I think reconnect to my 2 minute summary. So we have this method to find discoveries, which focuses on training the policy at test time, which is the difference with the state of the art that was not basically a training model, but also introduce two things. One is the entropic objective to favoring max rewards, and the PUCT balanced way of sampling or in general like, to balance exploration exploitation. The again, as a last thing, the insight here is the discovery process is different from standard reinforcement learning, and this is why standard reinforcement learning wouldn't work in this context. We need one very good solution, not many good ones on average. So we don't need an agent that can be very good on average. We need an agent that can come up with a very good solution, and then we basically throw away the agent itself. So design choices should actually reflect this, and this is reflected in the choices we made on the sampling and on the entropic objective. Everything is open sourced. You can easily run this with our code and you can implement new tasks very easily. We made this new API that should allow people to basically add their own tasks and just run them and see if they get a new state of the art. And yeah, thank you so much. Happy to answer questions now. Thank you again for inviting me.